So factoring is breaking up a number in its multiplication pieces. Basically, it's unmultiplying something. So if we start with an area, the area is 2x plus 6. We're going to unmultiply or break up the multiplication into its length and width pieces. Okay, and that's essentially what factoring is. We're finding out the length and width. And that's the kind of model that we're going to use when we talk about breaking up multiplication or factoring. So when we have this expression here, x squared plus 5x plus 6, basically we're starting with an area. Okay, so this is x squared, 6, and the 5x is a combination of these two. And we're trying to figure out what is the length and width of this shape, okay, of this rectangle. So if we find the common factor here, that is the common side length x. We find the common factor here, this is common side length of 3. And then going across, we can find our common side length of x here. Coming across this way, we get our common side length of 2. So 2x and 6 share a common side length of 2. And this is all going to match. So we have x times x is x squared, 3 times x is 3x, x times 2 is 2x, 3 times 2 is 6. And it gives us the factored form, or the length, x plus 3, and the width, x plus 2. And if we want to check this, we could just FOIL this out, right? First outside, inside, last. So first, x squared, outside, inside, last, gives us what we started with, x squared plus 5x plus 2. So this is then definitely the correct factored form. This is what we're looking for. We're looking for the length and width given that area. So same thing's happening here. We have our area, x squared plus 4x minus 12. Now we know the relationship is, we're basically looking for these two edge lengths that multiply to 6 and are going to give us these two areas of 3 and 2. So we can think of the same thing here. We're looking for an edge length, and this only works for x squared because we know that these two edges are going to be x times x to give us a square. And to give us an area of negative 12, one of these edges has to be negative, the other one has to be positive. And these two areas must add up to a positive 4x, and one of them being negative and one of them being positive. The only way to make this work then is we're going to use positive 6 to give us a 6x here, and negative 2 to give us a negative 2x here. So negative 2 times positive 6 is negative 12. These two areas add up to the positive 4. So there we go. We have our area involved here. So our length and width to give us that area. So x plus 6 times x minus 2. Okay, so there's our factored form. And notice that all we're doing is factoring. We're not solving for anything here. Okay, that's not an equation. If it was equal to 0, we can solve. So we can say x is equal to something, but this is just factoring, so we just leave it like that. And that's something I want you to recognize. When are you being asked to factor? When are you being asked to solve? When are you being asked to graph? And you're going to need to recognize the difference. So using algebra tiles here, okay, we're typically going to stick with the area model, but we should understand our algebra tile model. The area here is going to be 2x squared plus 4 x's, there's 1, 2, 3, 4, plus 2. If I want to factor this, I get an edge length of 2x plus 2, and the other edge length is going to be x plus 1. Okay, this is not fully factored because there is a common factor of 2 here, so I can factor that out and say that I have x plus 1, or 2 x plus 1 squares. Okay, which is true because if I rearrange this, really I could, if I shift this over, I could have 2 squares of x plus 1. Okay, I can have these, this is going to be 2x squared plus 4x's plus 2, and that's going to give me 2 squares, which is what my factoring certainly indicates. Okay, so this algebra tile model, the area is going to be x squared minus 4x plus 4. Okay, and I can see that my edge length is going to be x minus 2. I can see I have two negative x's here. And x minus 2. I've got two negative x's here. And it does give us a square shape because it's symmetrical both ways. Okay. Now the real main problem with factoring is going to be really how do we rearrange these square shape pieces, or the x pieces, or the rectangular x pieces, to fit them in, because we know the squares go in the top left corner, we know the ones go in the bottom right. It really is just figuring out how do we split up these terms here, because those are the terms that get added up to its like terms to give us the middle term. So that's really the dilemma that we often end up with when we're factoring. And that especially shows up when we are factoring an ax squared type. So when we're factoring an ax squared type, what we can do is we can kind of guess at this, because we do know that this has to be 2x squared. So we have to have 2x times x. And then we can guess at the factors of 3. Well, there's only one way we can do it, 3 times 1. If I do it like this, if I do plus 3 times 1, okay, I have a bit of a problem because I end up with x and 6x here. That's 7x, and that doesn't match my middle. So then I can just re-guess at it again and say, okay, well, it's got to be 1 and 3. And by guessing, I end up with getting 2x and 3x, and that's definitely the right way. So I've now factored this. I know this is going to be 2x plus 3, and then x plus 1. So that's the correct answer. So if you need to guess and test, nothing wrong with that. But we want a bit better strategy. Now this was an easy one because there's very little guessing to be done here. There's not very many possibilities. So what are some other strategies here that we can use? So I'm going to show you this property of this grid multiplication. Okay, so if I have some random multiplication, 20 plus 1 times 10 plus 5 or something like that. Okay, so I end up with this. This is going to be 200. This is going to be 10. 20 times 5 is 100. And 1 times 5 is 5. Okay, so this is just grid multiplication. You would have done this in elementary school. And this is all we're doing here. This is really just grid multiplication with variables. But there's a property here of grid multiplication in that this diagonal product, this is equal to 1000, is equal to this diagonal product, which is equal to 1000 as well. And it's always the case. Okay, there's a very simple proof to this, but the diagonal products of grid multiplication are always equivalent. Okay, well, how do we use that property then? So again, this is the property. The diagonal products of this box multiplication are equivalent. And that holds true whether we're dealing with numbers or variables. So how do we use that property to help us factor? Well, we're going to do this. If I multiply this diagonal product, I get 6x squared. And what I know is that whatever I put into here is going to multiply to 6x squared. Not only that, it has to add to the areas. These two areas have to add up to 5x. Well, the only way we can do that is we can just say that's going to be 3 and 2. 3x and 2x. Those equal, if I multiply them together, that's 6x squared, and they add up to 5x. So we can use this diagonal product here to be able to split the middle term. Okay, and some of you may have seen it showing up like this. I'm just going to leave it like that. Okay, so once we factor, we can just factor this straight across. Okay, this is the common factor here is x. The common factor here is 1. The common factor here is going to be 2x. The common factor here is going to be 3. So I end up with x plus 1 times 2x plus 3, which is correct. So some of you may have seen this diagonal product show up slightly differently, and some of you may have used this 2 times 3 equals 6. Okay, and really that's what we're doing. This 2 times 3 is the diagonal product. It's the same thing as happening here. We're just leaving out the x parts of it. And some of you use that 2 times 3 equals 6 to split up the middle term 5x into 2 and 5. Okay, and that's essentially the same thing, but this is a reason why we're able to do that. It's this property of this diagonal product of a box multiplication is equal to the other diagonal product, which allows us to split up this middle term. And that's the key to factoring these types.